Okay, so we're starting where we left off with stoichiometry. Again, stoichiometry is a little confusing in the beginning, but all you guys have to do is remember your different conversion factors, those different ratios that take you from grams to moles, from particles to moles, and don't forget molar volume. Don't be scared off by liters to moles or moles to liters. So Avogadro's number is a constant that's on your reference sheet. So is molar volume. You just need to know where to look for it. If you haven't taken a good look at that reference sheet, I suggest you do that today before you get to the exam, so that if you see something on the exam, you can think back, oh, I'm pretty sure that's on my reference guide, and you can get some help from your reference guide. So how do we go from grams to moles? Molar volume. How do we go from moles to particles? Avogadro's number. What is it? 6.02 times 10 to the 23rd. How do we go from liters to moles? 22. 22.4 liters per mole. Again, that's on your reference guide. So in stoichiometry, that's not where it's going to end. Now you have to go from moles of one substance into moles of a different substance. What do we use to get from moles of one substance to another substance? Mole ratio that comes from what? A balanced equation. So it's going to be those coefficients out in front of each of those molecules, whatever they are, and you are using those coefficients. Are you going to be able to tell if the equation is balanced or not? Yes, absolutely. If it has lines in front of each of the things, it's not balanced, and you're expected to balance it first. But if it has numbers in front of each of those things, or maybe one or two things, it's already been balanced, and you can use those mole-to-mole ratios. If you balance it, and then you recognize it's already balanced, but it's incorrect, which numbers are you going to use? The incorrect. You are using what the test gives you, even if it's incorrect. Because somebody made a mistake, they did not catch it, and that's what they used to get the right answer. So make sure that even if that information is incorrect, you can tell me about it later, but you are using what that test is giving you. And that has happened in the past, so be careful. Okay. Percent yield. We did that yesterday with the popcorn lab. So tell me how you calculate for percent yield. How do you calculate for percent yield? We did it with our stoichiometry lab as well last week. So you have two different things that you might have to deal with. Actual and theoretical. Which one is which? What's the actual amount? What you get in the laboratory during your experiment. What's the theoretical amount? What you should get. In an ideal world, if it was 100% efficient or it was a perfect lab, this is what you should get. So in order to calculate percent yield, you're going to take what you got, the actual, divided by the theoretical, and then you can either turn it into a percent or you can multiply by 100, and that will turn it into a percent. States of matter, this should be easy. Can you talk about the molecular activity of solids, liquids, gases, and plasma? Can you talk about the molecular activity of solids, liquids, gases, and plasma? Yes, you can. Which one has the highest amount? Okay, it's like videotaping the ceiling. Which has the highest amount of energy? Not gas. Plasma. You're close, Gracie. Plasma has the highest, then gases, then liquids, then solids, and lastly, Bose-Einstein, which you're probably not going to have a question about Bose-Einstein. Have you guys heard the terms heat of fusion and heat of vaporization? So the heat of fusion is the amount of heat it takes in order to melt something. The heat of vaporization is the amount of energy it takes in order to boil something. And these graphs look like this. So you have ice that heats to a temperature, and then it goes like this. The straight line is when ice is melting. So this is your heat of fusion right there. Then you heat the liquid water all the way up to here, and then this is where that water boils off. So this is adding heat. The temperature does not change until every single last particle that's a solid has phased into a liquid. Once everything's a liquid, then you can start heating your temperature again. And then up here, the temperature does not increase during the boiling process. Not until all of that liquid has phase changed into a gas can you then have those gas particles starting the process of heating further than this right here for ice would be 0 degrees, and this right here for boiling would be 100 degrees. So this graph, you might see a graph that looks like this that deals with adding heat and then phase changing. The temperature doesn't change during a phase change, not until all that material has turned into the new substance or turned into the new phase. And then again, you can heat up to the point of boiling, and then it remains a constant temperature throughout the boiling process. Specific heat just means how much energy does it take to heat that substance 1 degree. So 1 gram of substance, 1 degree Celsius. And then you guys have all heard the difference between endothermic and exothermic reactions, correct? What does endothermic mean? Say it again. It is absorbing energy so it feels colder. What does exothermic mean? Releasing energy, so you're going to feel the heat coming off of it. Okay, there are 2 other vocabulary words that are a little more up to date than endothermic and exothermic. You might see endergonic and exergonic, and that's just a wider range of different energies that could be released, not just heat. So endergonic versus exergonic are the exact same things as endothermic and exothermic. Everybody knows what STP stands for? Standard temperature pressure. What is standard temperature? 273 K or 0 Celsius. What is standard pressure? Nice. Tell me one of them.
101.3 kPa.
Perfect. If it's measured in kPa, it's 101.3. If it's measured in ATM, it's 1. If it's measured in millimeters of mercury or torr, it's 760. So it varies, and you can use your reference guide in order to figure out which one it is you might need. Behavior of gases, really we're talking about the gas laws. So does everybody remember that universal gas law equation? What if you don't? Where can you look? Your reference sheet. Okay, so Hunter, what is it? The gas law equation.
Pressure 1, volume 1 over temperature 1 equals pressure 2 over volume 2 over temperature.
Perfect. So P1 V1 over T1 equals P2 V2 over T2. You might encounter a gas law problem that doesn't go from one scenario into another scenario. There is also, and you have access to this, it's rare, but it's called the ideal gas law. And the ideal gas law is PV equals NRT. R is the constant. So if there is a problem that you have to use the universal gas law or the ideal gas law, they are going to give you R. You'll just plug it in. P stands for what? Pressure. V stands for what? Volume. N is the number of moles. How much stuff you're talking about. R is going to be given to you. T stands for what? Temperature. So any one of you can do multiplication. You're going to solve this like an algebraic equation. You're going to multiply, solve for whatever x factor they ask you, and then you might have to divide away to get x by itself. So again, the gas law, P1V1 over T1 equals P2V2 over T2, that's really what you're probably going to find yourself using more commonly than anything else. But the ideal gas law, you have this equation on the back of your periodic table. It's PV equals nRT. N are the number of moles. R is a constant, and they have to give it to you. You're not expected to know that. So you may or may not see that. And then lastly, talking about solutions, solvents, solutes, electrolytes, aqueous, molarity, molality, dissolving, concentrations, saturated versus unsaturated versus supersaturated. So there are a couple vocabulary terms that I just rattled off. Most of you probably know most of them. And a lot of solubility is kind of common sense. So on the solubility graphs, what is it if it's on the line? Saturated. If it's above the line, super saturated, below the line, unsaturated. How many grams of water are solubility graphs based on? 100 grams of water. So if your question says something about only having 40 grams of water or having 550 grams of water, you can set it up like a ratio. Whatever it is to the 100 grams, that's your graph. And then you can put X's to however many grams of water they're actually giving you. Any questions over this slide? Okay. So the last topic that we talked about was acids and bases, and then we did a little bit of nuclear chemistry as well. How can you recognize an acid? Starts with an H. How can you recognize a base? Ends with OH. That's called a hydroxyl. So when you have an H and an OH come together, what's a product that you get in an acid-base reaction? Water. Water can be both an acid or a base, depending on what kind of solution it's added into or what solutes are being dissolved into it. What color does blue litmus paper turn in the presence of an acid? Blue turns into red. What does phenolphthalein do in an acid? Stays clear. If it's phenol red, which is what you guys used Monday, what did that turn? Should have turned clear. Some of you said it looked kind of yellow. Okay, in the presence of an acid. If we're talking about bases, red litmus paper turns what color with a base? Blue. What about with phenolphthalein? What does phenolphthalein do in the presence of a base? It's really pretty. Bright pink. It turns bright pink. And then the phenol red also should either stay red or turn pink. Okay. Nuclear reactions. What types of nuclear decay did we talk about? Alpha, beta, positron emission, electron capture, and the last one, gamma radiation. What happens with alpha decay? What do you give off? What kind of particle? Helium, a helium particle. So alpha decay, you're going to have to subtract a 4 from the mass and a 2 from the atomic number to figure out what it decays into. Beta decay, you are adding a what? Proton. If you start with carbon, you add a proton and you end up with nitrogen plus this electron, or this beta particle, which is an E with a -1 charge. What's gamma radiation? Does it change anything? No. Gamma radiation doesn't change anything, but what is it? Super high frequency, super high energy, a little bit more dangerous. Okay? All right, half-lives, divide by 2 as many times as you need to. If there are 6 half-lives, you cannot take the substance divided by 6. You need to take the substance divided by 2, divided by 2, divided by 2, 6 times. And then make sure you pay attention to how long the half-life is. If there's a graph, whatever that first jump is, that's your half-life. So if it jumps from 0 to 33 minutes, that's your half-life. If it jumps from 0 to 5,730 years, that's your half-life. So be able to interpret those graphs as well. And then fission versus fusion. Which one do we do at nuclear power plants? Which one? Fission or fusion? Fission. We can split in power plants. We cannot join nuclei. We don't have the pressure. So fission is splitting atomic nuclei, and then those 2 nuclei have a lot of energy. Then they split the other atoms that are right next to them, and it's a huge snowball effect. Fusion only happens out in outer space with stars like the sun, where you have hydrogen atoms fusing into helium, and in the process they give off that electromagnetic spectrum. That's another vocabulary word. Does everybody know what the electromagnetic spectrum is? What are some things that are given off in nuclear fusion? What are some parts of the electromagnetic spectrum? We just talked about one, super high energy, super dangerous, super high frequency, gamma radiation. What else? Radio waves, microwaves, X-rays, ultraviolet radiation, infrared, visible lights. So, does that sound familiar? You guys are dead today. Wake up.